Hello. In this video, I'm going to be going over question 5, part 1. And I'm also, in the first half of the video, going to be going over a lot of information theory that the professor and I both think is critical to know in order to stay up with the course. And it's also going to be very important to know for the test. Funny coincidence. In the next video, we're going to be going over question 5, parts 2, 3, and 4. And in the video after that, we'll be doing question 5, part 5. Now, let's get started with the information theory. I'll spend the first half or probably more of this video going over just information theory and connecting all the ideas to each other. So if anything about the information theory slide deck is unclear to you, or if you just want a refresher, this will probably help you. All right. Now, the first concept in information theory that we need to know is the concept of information. I know, sounds very like a no-brainer. So information we write as I of x, and that is equivalent to log of 1 over p of x. All right, so what does this mean? Well, if you want an in-depth explanation of why this is, you can go to the slides. But if you want an intuitive explanation, you can think of information as surprise at a certain event happening, right? If an event happens, let's say a meteor falls in New York City, well, that's really surprising, and that's also really unlikely. Unlikely events are more surprising. Unlikely events give us more information because they happened, right? If I challenge Professor Wu to a basketball shoot-off contest and I lose, that doesn't give us a lot of information because that was almost a certainty. But if I challenge Professor Wu to a basketball shoot-off contest and I win, well, that gives us a lot of information because maybe you can derive something from that, or maybe it's just very surprising. But either way, that's a lot of information. As for the reason why the log is there, well, we like to work in log probabilities. That's kind of it. Log likelihood is just great. We should always work with that. All right. So now that we've identified what information is, let's move on to the next concept, entropy. Entropy we define with the h of x, because physics beat us to E, so we can't use that. And entropy is just the expected information of an event. So it's E of I of x. Now, hopefully you know the formula for expected values at this point. But if you don't, I'm going to write out the whole thing just in case. Now you remember that expected values is always a piecewise because you have to define it differently for discrete and continuous variables. So for discrete, we have a sum. And for continuous, we have an integral. And that's the only difference between the two. The rest is the exact same. P of x, log of 1 over p of x. And I guess there's a dx on the integral, so maybe I lied, but it's the same. Now, if you want to see how this relates to the general formula, remember that E of x, or actually, I'll just do E of x equals, I'll do the integral. Integral of x f of x dx, right? This is the formula for expected. Why am I? I'll just do that there. So it's not, doesn't look like there's an x squared there. So this is the formula for expected value, and that is what entropy is. Discrete and continuous. Anyways, let's move on to the next idea, which is cross entropy. Cross entropy is sort of like covariance. If you think of entropy as variance, you can think of cross entropy as covariance. They're actually almost exactly the same in that regards. If you don't want to think of it that way, you can also think of it as cross entropy is a measure of the distance between two distributions. And specifically, it measures the difference between the two distributions. So, h of p, q, we have two different distributions this time. And really all it is actually, another way to think about it, is you calculate the entropy, but you use the expected information of q of x, but you use the probability of p of x happening. That might not make a lot of sense, so let's just write it out real quick. So sum of x, we have p of x and the log, but we have the probability, we have the expected information actually of Q of x using the probability of P of x. So that's cross entropy, and it's a measure of the difference between two distributions. Now, this is extremely important to know. You might even just want to memorize this, even though it's you can kind of get here from knowing information, right? I'm trying to establish a chain, right? From information, you can know entropy. From entropy, you can know cross entropy, right? And so this is one of the most important objectives in machine learning, and it's used so commonly. But what's the next concept? What do we move on from here from? Well, the next concept is KL divergence, right? KL divergence is the excessive entropy from cross entropy. So here's the formula. This might not make sense, so let me explain it, okay? So KL divergence is a distance metric between two distributions. Cross entropy is not easily bound, and so what we want to do is we might want to define something which has a lower bound of 0, and that is what KL divergence is. Because when when P and Q are equal to each other, then H of P comma Q, that's just H of P, right? And it turns out that cross entropy is actually always larger than entropy, right? Or it's equivalent to. So in this case, KL divergence, its lowest bound is 0, right? And I'll just do x here. The upper bound is different, and you don't really need to know that. But you can also think of cross entropy as sort of like an additional entropy when you add QX into a system, right? And then you can think of KL divergence as the excessive entropy. Either way, there's a lot of ways to think about KL divergence. One of the easiest ways to think about it is just the difference between cross entropy and entropy, right? So the next concept I want to go over is mutual information. This is the last concept for this video. So mutual information, you notice I left a lot of space here. Well, that's because I'm going to be deriving what KL divergence looks like. I'm just going to be doing a bunch of math. All right, so let's just pull out, let's expand these into their constituent parts. We have the sum of x, P of x, log 1 over Q of x, plus, nope, not plus, minus, sum of x, P of x, log 1 over P of x. Now what we can do is we can group by the common components. So sum P of x log 1 over Q of x minus log of 1 over P of x. And once we do that, we can then use a log rule here. Now, if you remember log, let me write this up here. Log of A divided by A over B is equivalent to log of A minus log of B. That's a log rule. You should also remember a lot of the log rules as well. They'll be fairly important to know. So in this case, we now know that we have this nice simple equation. Log of P of x over Q. All right, so now that we have that, let's keep going to mutual information. The best way to think about mutual information is that it is the KL divergence between P of xy P of x, y, and P of x, P of y. So let's take the formula knowing that. So Kale divergence says for all entries, so because we have x and y, we're going to need two summations, right? Then let's do P of x log P x y over P x P y. And that is our formula for mutual information. Now remember, this is the Kale divergence between P of xy and P of x, P of y. All right. So one thing to remember before I start this problem is that when I equals 0, so when mutual information is 0, that means that P of x, y, so let's actually do this, mi of this implies, so if mutual information of xy equals 0, then that implies that P of xy and P of x, P of y are equivalent. And that means that there's complete independence happening here. We're not going to really use the concept of complete independence for this test, but in the future, being able to verify and know that there's complete independence is a very powerful thing to know. All right, so now that we've defined what mutual information is, let's finally do question 5, part 1. Calculate the mutual information I of x, y. So let's first talk about how we're going to do this. And while we do that, I'm going to write out the sums of all the y's. So y, this row is 0.2. This row is 0.3. And the next row is 0.5. And then for the columns, I'm going to do the sums of the columns as well. So 0.3 and 0.7. All right, let's go back to our mutual information formula. So mutual information says that for every entry, we're going to be using this formula. There are 6 entries in our table, so let's get started on that. If I remember correctly, what we can do when we're doing this, we can, if we want to do this on paper quickly, we can write out the entries by their probabilities individually in the same order. So 0.1, 0.1. Actually, let's go through a single example first, and then I'll write out the whole thing real quick. So probability of x comma y, we're going to do the first entry, that is x equals good and y equals ex. You see the probability of this is 0.1. So I've written 0.1 here. Then we multiply that by the log of the same number is on the top in the numerator inside the log. So it's 0.1. And the bottom is the probability of x and the probability of y. So the probability that y equals ex, the reason why I wrote these out earlier, is 0.2. And the probability that x is good is 0.7. So 0.7 times 0.2. All right. Now that I've written out one part, we need to write out 5 others. So I'm going to write them out very quick and show you how I like to do this as fast as possible. I like to write out the P of x, y's in the same order they show up in the table that I'm given. And then you can just fill in the blanks from there. So log and we know that the numerator is always the same as the coefficient of that, I guess, block. I don't know the mathematically correct term for this. So 0.2, 0.4, 0.1, 0.1, 0.1. And then for the denominators, all we need to do is you multiply the column-wise sum and the row-wise sum of the coefficients in this case, because we just copied the coefficients down. So we have 0.7, 0.7 times 0.3 times 0.5, and then this would be 0.3 times 0.2, 0.3 times 0.3, and 0.3 times 0.5. Now, this is our mutual information. I don't need a plus there. We expanded the sums, and this is a reasonable stopping point for the test since you won't have any calculators. If you wanted to, you could simplify the numbers inside of the logs, but I think that's unnecessary, and we're not going to require you to do that. All right, now this has been how you find mutual information and as well as a whole bunch of information theory. All right, good luck on your tests, and I will see you in the next video about question 5, part 2, 3, and 4.